Hi, we're going to work through a couple of examples of related rates problems. Hopefully you've had a chance to look at the document outlining the process by which we're going to solve these problems. And you've also gotten the page with the examples on it. So let's work through a couple of these. I'm going to try to follow the outline process that I did post. So our first step is really to read the question and try to get just a feel for what it is that we're going to be looking at. And so I say in step one, we're going to identify all quantities that are changing over time and give names to those variables. So let's read this question. We're throwing a stone into a pool, and hopefully you can visualize a ripple forming in the shape of a circle. And we're told that the radius of the ripple is growing at a rate of 2 centimeters per second. And we're trying to get a handle on the rate at which the area of the enclosed circle is growing when the radius is 9 centimeters. So reading this question, we want to be looking for words like increase, decrease. The word rate often appears in a lot of these problems, and that's something that we want to try to focus on. And so if we're thinking about the quantities that are changing, we get here radius growing, and we're told the rate at which it's growing, and then we're asked about the rate of growth in the area of the circle. And so those point us to identifying the quantities that are changing over time. So we'll say the radius of the circle, we'll call it R, and the area of the circle, and I'm going to call that capital A. Our next step, I like to try to encourage us to interrogate ourselves and try to ask questions about what we've read. And so we want to ask ourselves, what is it we're trying to find? What rate of change are we looking for? And so hopefully in this problem, we look at the question, we see we want to know the rate at which the area is growing. Now we're going to represent our derivatives in these problems, usually in the Leibniz notation form, the fractional form. And so I want dA over dt, the rate of change in the area when the radius is 9 centimeters. And then we want to ask ourselves, what are we given? Well, the information that we have is that we've got a circle, but more importantly, we're told the rate of change in the radius of the circle. And so if we're asked to write down what we know that dr over dt is equal to 2 centimeters per second. And I'm going to include units as often as I can in my work, because I think the units can really help us plays an important role in helping us figure out where to plug in things. And we want to be thinking about what kind of units am I looking for in my answer. And then we want to ask ourselves, how are the variables related? And this is one of those cases where we want to have a formula from geometry. The relationship between the area and the radius of a circle is that the area is equal to pi r squared. And now it says implicitly differentiate this equation with respect to time. And so, as I noted in the description, one thing that's different about this problem from the ones that we saw in the previous section is that time, the variable time, which often we represent with the letter t, does not appear in our equation. And so both a and r are functions of time. And so whenever we differentiate any variable that's a function of time, we're going to include its derivative. And so the implicit differentiation, derivative of the left, the derivative of a with respect to time, we represent as dA over dt. And then pi r squared is a composition where the squaring function is outside, r is inside. And so I'm going to get 2 times the inside times the derivative of the inside. Next, our next step is to substitute in what we know, to try to find out what we want to find. And so what we're told is we can substitute in for r. We know that r is 9 centimeters, and we're told that dr over dt is 2 centimeters per second. And so we can substitute that information in. dA over dt is pi times 2 times 9 centimeters times 2 centimeters per second. And if we multiply that all out together, we get 36 pi square centimeters per second. And then lastly, I suggest that we write a sentence that answers our question. And so the area of the circle is changing at a rate of 36 pi square centimeters per second when the radius is 9 centimeters. So notice I've gone through all the steps in the outline. I've read carefully, I've identified the quantities that are changing, I've given them variable names, I've identified what it is that I want to find, represented it symbolically, and then I write down the information that I'm given about other rates of change. I've come up with a relationship between the quantities that are changing. I've implicitly differentiated, and then I've substituted in the values that I know. And I found the rate of change that I was interested in determining and reported it back. Next, we're going to look at a second example. Air is leaking out of a spherical balloon at a rate of 48 cubic centimeters per minute. At what rate is the radius of the balloon changing at the moment that the volume of air in the balloon is this sort of odd number, 2,304 pi cubic centimeters? I've chosen that number to make some calculations a little bit later on in the problem nicer. So we want to read and figure out what's changing. And so we've got air leaking out. So the amount of air in the balloon is changing. And we're interested in the rate of change in the radius. So one of our variables, one of the quantities, is going to be the radius of the balloon. And even though the word doesn't appear in the first sentence, it appears later on, we're told that the volume of air in the balloon that we're interested in at the moment we're interested in is 2,304 pi cubic centimeters. So volume is the other variable that we're interested in. That's the amount of air in the balloon. What do we want? Well, we want to find the rate of change in the radius. So we want dr over dt when the volume is 2,304 pi cubic centimeters. What do we know? Well, we know that air is leaking out of the balloon. That suggests that the rate of change in the volume is negative. And here's where cubic centimeters per second goes. So we know that dV over dt is minus 48 cubic centimeters per second. We might have to look this up, but there's a formula for the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. And then we want to differentiate this implicitly. The derivative of the left is just dV over dt. The derivative of the right, I'm going to get 4/3 times 3 times, and then r cubed. This is a composition again, so I'm going to get 3r squared dr over dt as my rate of change on the right, my derivative on the right. And so I can simplify that a little bit. The 3's cancel, and I'm left with 4 pi r squared dr over dt. And now I want to try to substitute in my information. I know that dv over dt is minus 48 cubic centimeters per second, so I'll be substituting this in right here. This is what I want. I want dr over dt, and so I'm going to have to figure out what to substitute in for r squared. I know the volume, but I don't know the radius. And so this is one of those cases where we're going to use our formula a second time. And so we can use this formula to figure out what the radius is. And so I'm going to multiply both sides of this equation by 3/4 pi. Three over 4 pi. Pi's cancel. And now, if I multiply this out, I get 1728 cubic centimeters equals r cubed. And then when I take the cube root, I get that r is equal to 12 centimeters. And so I'm going to substitute that in right here. So when I substitute my values in, I get negative 48 cubic centimeters per second equals 4 pi times 12 centimeters quantity squared times dr over dt. And so I'm going to, if I multiply 12 centimeters and I square that, I get 144 square centimeters. 4 times 144 is 576. Excuse me. And so I get dr over dt is equal to negative 48 over 576 pi. And now I've got centimeters cubed per second over centimeters squared. So it's going to cancel out 2 of those with this. And if I simplify my fraction, I get negative 1 over 12 pi, and my units are going to be centimeters per second. And so I can write down in my sentence the radius of the balloon is decreasing at a rate of negative 1 over 12 pi centimeters per second when the volume is 2,304 pi cubic centimeters.